Hello everyone. In this video and the next several videos, we are going to talk about some important topics in linear algebra, which is basically working with matrices and vectors. So in this first video, first we start with basic definitions, arithmetic, and some other important notions, and then we move forward to more advanced topics. So you might wonder why we use linear algebra and where we use linear algebra. So linear algebra and working with matrices is important because it has so many applications, especially in engineering when we are dealing with systems that have lots of inputs and outputs, and you want to write their equations, their governing equations, in a concise form, or in robotic systems when you are dealing with rotations and translations and you want to combine again everything into a concise format. These matrices are used a lot. So it is important to learn about linear algebra. But we know about the notion of a vector, right? Vector is a 1D arrangement of objects, correct? Basically either in a row or in a column. So matrix is an extension of that, is a 2D or multi-dimensional version of that. A regular matrix, when we talk about, is a rectangular arrangement of objects into a number of rows and a number of columns, okay? Then these objects could be basically anything. They could be numbers, they could be variables, functions of something, right? They could be anything. Most of the time what we deal with are numbers or functions of some other variables, but it could be anything. So the first thing that we need to know about the matrix is the dimension of the matrix, and we show it with two subscripts. We say this matrix is M by n when it has m rows, as you can see, and it has n columns, okay? Or we can show it with a notation like this. Say this is the component or entry aij, where I goes from 1 to m, okay, and j goes from 1 to n. So first of all, each one of these elements of the matrix is called an entry. Okay, so each one of them is an entry. And then when we show an entry, you see we use two subscripts. The first one is the row index, the second one is the column index, okay? So this is how we show a matrix and its entries. So when we say A, for example, 1, 2, it means row 1, column 2, which is this guy here. So this is what? This is the definition of a matrix. Now, depending on whether it has more rows, more columns, or it has the same number of rows and columns, we can give a different naming to the matrix. So if m is equal to n, so it has the same number of rows as columns, then we call the matrix what? We call it the square. And of course the definition completely makes sense, right? It is a rectangle with the same size in both directions, so we call it a square matrix. 2 by 2, 3 by 3, 4 by 4. Now, if m is not equal to n, then of course we call it a non-square matrix. And there are some terminologies that you might hear somewhere, so I'll tell you about it. So a non-square matrix can be of two types. Either m is bigger than n, which means your matrix is basically like this, correct? Like 4 by 2, 6 by 3, right? 10 by 4, something like that. When that's the case, we might call the matrix a tall matrix. Okay, so if you ever hear this word, you know what it means. And on the other hand, if n is bigger than m, then it is going to be something like this, right? Like 2 by 6, 3 by 10, right? 4 by 11, something like that. And we might call that matrix a fat matrix. So again, don't be surprised when you hear these terminologies, okay? These are some terminologies. You don't have to really, you might just call them non-square matrix. So that's a square versus non-square. Now, when your matrix is square, there are lots of other things that you can define for it. So when it is a square matrix, so if m is equal to n, it is a square matrix, then we define the main diagonal for the matrix. Let's say, for example, the matrix is what? N by n in general. So the elements that have the same row index as the column index, like A1, 1, A2, 2, A3, 3, all the way to ANN. These entries in the matrix, we call them what? The main diagonal. Okay, so this guy is your main diagonal. These entries here are above diagonal. These elements here are below diagonal. Okay? The sum of the elements on this main diagonal are called trace. So first main diagonals, they are all like AII. And summation of this AII from 1 to n, this guy is called trace of this matrix A. Okay, so trace is sum of the diagonal elements. Now, do we have, here we say main diagonal, do we have any non-main diagonal? Yes, this guy here, the elements on this can be called the opposite diagonal or the non-main diagonal. Okay, so on this one here, only one of your entries typically might have the same row and the same column number, not always. For example, if it's 4 by 4, it's not going to have any. If it's an odd number, 5 by 5 or 3 by 3, then only one of the elements will be common to the main diagonal. Anything else will not have the same row index and the same column index. So that's about trace main diagonal. Now, if your matrix happens to have only non-zero on the diagonal and nowhere else, so anywhere outside the diagonal you have 0, okay? So your matrix is like a bunch of non-zero elements, A1, 1, A2, 2, all the way to ANN, but everywhere else is completely 0. Any element outside diagonal is 0. Then we call this a diagonal matrix. On the other hand, if only one of these two is 0, so your A looks like what? Looks like a bunch of non-zeros on the diagonal, and then what? Then also some non-zero other elements like A1, 2 all the way to A1n, and then it goes all the way to here. If it's something like that, but anything below the diagonal all 0, we call this matrix upper triangular. And similarly, so if I want to write it here, in terms of the entries, here any aij is equal to 0 as long as I is not equal to j. For the upper triangular, we can say any aij is equal to 0 as long as I is bigger than j. So the elements below diagonal, they have a bigger row index than a column index. And similarly, I can define a lower triangular when you have on the diagonal and below the diagonal non-zero elements in general. It doesn't mean all of them are non-zero. I'll show you. I, n, and 1. Then everything else here is 0. Then this guy we call lower triangular. And again, we can say this is aij equals 0, where j is bigger than I. Now, when we say these numbers are non-zero, we don't mean all of them. Some of them can be non-zero, and we still call it lower or upper triangular. But the one below, they should all be 0. So if somebody asks you, hey, what about a matrix like this? 1, 3, 5, 0, 0, 0, 6, 0, and 4. Is this upper triangular? Yes. It doesn't matter whether this guy is 0 or not. As long as not all of them are 0, we still call it upper triangular. The important thing is the lower part is all 0. Okay, so keep that in mind. Not all of them should be non-zero. Okay, so these are important initial definitions that I mentioned for you. Definition of matrix, a square versus non-square, main diagonal, triangular, diagonal matrices, and trace. Let's move on to the next part. There are some special type of matrices. Identity matrix, zero matrix, and a sparse matrix. So identity matrix I is a matrix that is first of all a square, second of all diagonal. So it is definitely a diagonal matrix, and then all of the entries on the diagonal are 1. And everywhere else it is all 0. Okay, we call it an identity matrix. What's so special about it? I'll show you in a second. We have a zero matrix. The zero matrix does not have to be square. It can be a rectangular matrix. It can be a non-square matrix, okay? The only important thing about it is all of the numbers in it are 0. All of them. Okay? And sparse matrix is what? A sparse matrix like A, there is no general definition, but in general we call a matrix sparse when it has lots of its element to be 0. So it only has a few non-zero values. Something, for example, let's say if it's a 3 by 3, I have something like 0, 2, 0, 4, 0, 0, 0, 0, 3, something like this. So only a few elements are non-zero, the rest of it is 0. Now, those elements are not necessarily on the diagonal below or above it. They can be randomly spread over the matrix. Now, how many of these have to be 0 to call it a sparse? As I said, there is no general consensus on it, okay? But typically, one of the things they mention is the number of non-zero elements should be similar to the number of rows or the number of columns. And by the way, a sparse matrix does not have to be square. So let me here add a little bit more to it. So let's say 6, 0, and 0. So first of all, it doesn't have to be a square matrix. And then they say the number of non-zero elements in it should be similar to what? The number of rows or the number of columns. So if it's a 3 by 4, you want to have not really much more than 4 non-zero elements. Okay, if half of it is non-zero, you're not going to call it a sparse matrix. But again, is there a specific number? Not really. But these are matrices that have lots of zeros in them. And what's so special about them? The special thing is when you want to store them, you don't need to store each and every one of the numbers. All you need is to store the non-zero numbers and where they are. Okay, so storage of them takes a lot less size of your memory. But accessing them, you need to keep in mind where they are, and so when you want to work with them, do arithmetic and so on, it's quite more difficult actually than a regular matrix if you store them that way. And we also have a definition called sparsity. So sparsity, which is basically, as you can see, it means sparseness, how much sparse it is. Sparsity, it is basically the number of zero entries to the number of total entries. So for example, for this matrix, which has 12 elements, you see 8 of them are 0, and it has 12, so it's going to be 8 divided by 12. And if you want, you can multiply it by a percentage. So it's like 67% sparse, okay? And if a matrix is not sparse, in general, we call it what? So opposite of sparse, we call it dense. So just another terminology for you. Okay, now I'll tell you in a minute what's special about these two matrices, I and O, okay? The zero matrix and the identity matrix. But the sparse, I told you, the main thing about it is the storage of it does not take a lot of memory. So now let's look at the arithmetic of matrices and see how we can add matrices, how we can subtract, multiply, and raise them to the power. So first of all, when we want to add or subtract two matrices, they have to be the same size. So if C is equal to A plus or minus B, A and B have to be the same size, both, let's say, m by n. The result is going to be the same size as well. And then you can say that each entry in C is equal to what? The same entry, the same row and column index in A, plus or minus the same row and column index in B. So it's basically adding corresponding entries together or subtracting corresponding entries together. It's not really such a hard thing. So if I have 2, 0, 4, and 6, and then subtract it from 3, 5, 1, and -1, all you need is to just subtract corresponding entries. So it's going to be 2 minus 3, which is -1. Then you have 0 minus 5, which is -5. Then you have 4 minus 1, which is 3. And then you have, let's say here, 6 minus -1, which is 7. Or if you want to add, you add corresponding elements, okay? So addition and subtraction is quite easy. Multiplication. There are two ways that you can multiply. One of them is you multiply the whole matrix by a single scalar number. The other one is you multiply two matrices together. So if you want to multiply whole matrix A by a scalar C, so C is just a single number and A is a matrix m by n. If you call the result matrix B, of course it has the same dimension as A, and then entry ij in matrix B is the same as entry ij in matrix A multiplied by that scalar C. So basically multiply that number C to each and every one of the entries in A, that gives you B. So a scalar multiplication by a matrix is quite easy. Now when you multiply two matrices together, so you have matrix A and matrix B, and you multiply the two matrices together to get matrix C, now there is some specific rule that you have to follow. What is that? The rule is this: when you multiply two matrices together, the number of columns in the first one, it has to be the same as the number of rows in the second one. So if first one is m by n, you can only multiply it by an n by something else. So these two Again, columns of first one and rows of the second one have to be the same. I'll tell you in a second why. And what is going to be the result? The result is going to be those two entries in A and B that are not the common number. So it's going to be M by P. Okay, now what is it that you're doing and why it's going to be like this? Well, basically when you're doing it, so let's say this is matrix A. It has m rows and n columns, so it is like A11, A12 all the way to A1n. Then you have A21 go all the way to MA, M1 all the way to MAN, okay? You multiply that by matrix B, which is n by P. So you have B11, B12 all the way to B1P, then B21 all the way to N1, Bn2, B22, B2P, and Bnp. When you do that, what you're doing is, let's say when I want to get my first entry in matrix C, how do I get this element 1, 1 in matrix C? So what I do, I take the first row of matrix A and multiply it. What do I mean by multiply? I mean dot product by the first column in matrix B. So it's going to be dot product between these two, dot product of first row by first column. And of course, the result is going to be a single number, which is going to go to what? To C11, right? Let's say when, for example, you want C M by P, correct? What would you do? You take the mth row of A by the pth column in B. Again, you dot product them, and the result is going to go here. Okay, so now why should they have the same? The first one, the number of columns in first one and the number of rows in the second one should be the same. That allows for these two vectors that you are dot producting to be the same size. If you look, this one has n entries and this one also has what? N entries. And you know, when you dot product two vectors, they have to have the same length. So because they both share n in them, that allows for the dot product to happen. Otherwise, you couldn't. And clearly, you see why the result is going to be CMP. Okay? So if I want to write it in terms of entry, Cij in matrix C is going to be summation of Aik times Bkj when k goes from 1 to n. And this is the definition of what? Column I of matrix A and row I of matrix A and column J of matrix B. That's the dot product of those two. Okay, so this is how we perform a matrix product. Now let's look at a simple example here. So I'm gonna go ahead and multiply, let's say a 3 by 2. So 1, 2, 0, 4, -1, and 3. So this matrix is 3 by 2, and then let's say I multiply that by a 2 by 4. So 2, -2, 3, or let's say 5, 0, and then 1, -1, and then let's say -3, and let's say 6. Okay, so here we have a 2 by 4, clearly you see the 2's match, and the result should be a 3 by 4. So it should be something like this. Okay, now how do I get each and every one of the elements? So first, let's say element 1, 1. So I do a dot product between the first row and the first column. It's 1 times 2 plus 1 times 2, so you get a 4. Then you do 1 time, then you go first row and the second column, right? So negative 2 and then negative 2, that's negative 4. Then you go first row and the third column. You'll get what? 1 times 5 plus 2 times negative 3, so that's negative 1, and then you go with the fourth column, which is going to be 0 and 12. Okay, and then you carry out. Now you go to the second row of A and repeat the procedure. Now you go to, again, the first column, you do that, you will get a 4. Then you go to the next one, you'll get a negative 4. You go to the third one, you will get a negative 12, and you go to the last one and you will get 24. And you repeat that for the last row. So again, go with the first column, you'll get a 1, then you go with the second one, you'll get a negative 1, you go with the third one, you'll get negative 14, and finally you go with the last one and you'll get 18. Okay, so this is multiplication of matrices, and it's quite clear what we are doing, but it is a little bit more involved than just adding or subtracting. Now, what about power of matrices? So when I say matrix A to power 2, what does it mean? It means A times A, of course. If it's power 3, means A times A times A. So the same way we define power for numbers. Now, there is one important thing. When you multiply A by A has to be a square matrix. Why? Because if it is a rectangular matrix, M by N, correct? You cannot multiply when M and N are different, right? You see, these two have to be the same number, and they are not. So if you want to do it, then M and N should be equal. So the only way that you can raise a matrix to power 2 is that the matrix has to be a square matrix. Okay? So that's about raising it to an integer power, 3, 4, 5, positive integer. Now you might say, what about A to the power 0? Well, A to the power 0, we define it as the identity matrix. So if this A is an n by n, we raise it to power 0, it's going to be an identity matrix n by n. Good? Now what about fractions? Can we do fractions? For example, what is A to the power 1/2? What is the square root of A? Well, calculating that is not as trivial as just multiplying A by itself. Why? Because whatever this A to the 1/2 is, when you multiply it by itself, it should give you the original matrix A, right? So let's say this matrix A is, for example, 1, 4, 3, and 5. Good? Now, if this is matrix A, my question is, what is the square root of A? Well, here, you know that the square root of A has to have the same format as A. So if it's 2 by 2, it's going to be a 2 by 2 matrix. And let's say it has 4 unknown entries, A, B, C, D. So if you multiply it by itself, A, B, C, D, the result should be what? The result should be as 1, 4, 3, 5. So if you do so, what will you get? You will get A squared plus BC is equal to 1. Then you will get AB, correct, plus BD equals 4. Then you get CA plus DC equals 3. And then you get CB plus D squared is equal to 5. So you get a 4 equation, 4 unknown set of nonlinear equations that you have to solve. And solving that has some specific algorithms, numerical and analytical, but in general it's not as trivial. One of the cases that these fractions are easy to do is when the matrix has what we call eigenvalues that are not zero and they are distinct. In that case, calculating any power of a is going to be easy. What is that? We'll get to it. It's one of our future lectures, eigenvalues of a matrix, and then we'll see how we can use those to use any power of a. So that's about raising it to a power. Finally, division. Do we have division for matrices? So do I have matrix A divided by B? The answer is no. In linear algebra, we do not divide two matrices. Okay, so we do not define this. But if you use MATLAB, and by the way, MATLAB is a very, very good software for matrices. As you know, the name MATLAB is what? When you say MATLAB, it is equal to matrix, and then what? Laboratory. Okay, so this is the math part of it, and this is the lab. So it is really based on matrices. So it's very good to work with matrices, and when you want to work with it, you need to know matrices well. Okay, but if you try something in MATLAB, let's say A equals 2 and 3, semicolon 1, 5, semicolon 6 and 0, right? By the way, in MATLAB, whenever you define a row, as I mentioned in my MATLAB videos, between the elements in a row, you can use a space or you can use comma. And between each a row and the next row, you use a semicolon. Okay, so A here is a 3 by 2. Now for B, I define, let's say, a 2 by 2 matrix. Let's say 2, 1, and then 0 and 6. So 2 by 2. So can I divide A by B? Well, ideally, based on what we said, no. We don't even define division by matrices. But if you do it in MATLAB, it gives you something. Right? And if you divide B by A, it gives you something else. Okay, well, of course, they should be different. But first of all, why did it allow it? Second of all, why the dimensions are this way and why the numbers are this way. So what is it that MATLAB is doing? It is basically using inverse and pseudo-inverse, and I'll tell you later. So if B is a square matrix, but just I mentioned it briefly, if B happens to be a square matrix, when you say, and let's say A is some n by m. Okay, when you do A divided by B, what it does, it actually multiplies inverse of B times A. And you say, now what is inverse? I'll show you. Inverse for basically matrices acts like 1 over the number for scalars. It acts like the reciprocal. Okay, so we'll talk about it later. Okay, we have a special video on inverse and pseudo-inverse. If B is not a square matrix, then we have to calculate something called pseudo-inverse, and as I said, we'll go over that. So don't rush. But we'll talk about what MATLAB is actually doing. Okay, so we really do not, in linear algebra, define division of matrices. So that's one thing. Now, when you have matrices, some properties about this multiplication, addition, subtraction, and so on. So one of the very important things is when you multiply two matrices, A times B, this is not equal to B times A. Okay, so the matrices product does not have the commutative law. You cannot reverse the order. First of all, sometimes it's not even impossible to do the other one, right? So if this is m by n and this is n by p, you can do it. But if you do backwards, it's going to be n by p times what? M by n, and clearly m and p, if they are different, it's impossible to do so. So if they are a square, only if they are both a square and the same dimension, then yes, you can do both, but again, their entries are going to be different. Okay, so in general, A, B, and BA are not the same. Now, when you want to multiply A by B plus or minus C, you can definitely use what? A times B and then plus and minus A times C. So product with respect to addition or subtraction has the distributive law. And also the associative law. So if you want to add A to B plus C, can you first add B and C to A, or first add A and B, then add it to C? Yes, you can do that. Okay, so the order doesn't matter, and the same thing for the product. If you want to multiply A by product of BC, instead you can first multiply A and B, then multiply it by C. Okay, so the product or the addition or subtraction, they have what? They have the associative law. Product with respect to addition subtraction has the distributive law. The product itself does not have the commutative law. The addition does have the commutative law. So A plus B is the same as B plus A. But of course, A minus B is not the same as B minus A. Right? What they are is they are negative of each other, which means if you multiply this whole thing by a -1, you get the other one. Correct? But in general, the subtraction does not have the commutative law. Okay, so we keep those in mind. One other thing now about going back to those identity and zero matrices, right? We say these are special matrices. Why are they special? Well, if we multiply matrix I by any other matrix that we can multiply, the result is going to be the original matrix. So if I multiply A by I, and A is, let's say, an m by n multiplied by an identity matrix n by n, the result is going to be A back again. So multiplying by I is not going to change the matrix. So I can say this I matrix corresponds to what? Corresponds to number 1 for scalars. When I multiply a scalar C by 1, I get C. Right? That's why we call it identity matrix. And what's special about the zero matrix? When you add or subtract the zero matrix to or from a matrix of its own size, correct? So this is the matrix with all zero entries. The result is going to be A. So it's not going to affect addition or subtraction, correct? So this is similar to number 0 that we had in scalars. Okay, that's why these two matrices are special matrix. Okay, so now let's move on to the next topic, transpose, symmetric, and skew-symmetric matrices. So when we say transpose of a matrix, we mean that if B is transpose of A, first of all, we show transpose by a superscript T, and it means we have basically swapped the rows and columns of A to get B. So if A is m by n, then B is going to be n by m. And as I said, it means swapping the rows in A to get B. So for example, the first column of A, you made it what? The first row of B. The second column of A, it's second row of B, and so on and so forth. Or another way to look at it is if they are diagonal, you can basically swap the elements that are mirror image of each other with respect to the main diagonal. But in general, that's all it is, swapping the rows and columns. So for example, if you have a row vector, you know a vector is a special type of matrix, right? When I say 1, 2, and 3 transpose, that means what? That means a column vector 1, 2, and 3, right? Or if I say, for example, 2, 1, 6, 0, 5, and 4, when I say transpose it, it means what? This guy is a 2 by 3. The result is going to be 3 by 2. And you take this first column and make it the first row. You take the second column and make it the second row. And then you take the third column and make it the third row. Okay, so that is transpose of a matrix. It has lots of applications. As we go forward, I'll show you. By the way, before I move forward, a couple of properties of the transpose. First of all, if you transpose a matrix twice, you get the original matrix back. Then if you transpose the addition or subtraction of two matrices, the transpose is going to be applied to both of them, and then you can add or subtract the transposes. And if you apply transpose to the product, like AB transpose, the result is going to be the transpose of the second one times the transpose of the first one. So when you apply transpose to a product, the order is reversed. Okay, this is AB, this is B transpose A transpose. Okay, so this is another property of the transpose which you can easily prove. So these are some important things about transpose. Now, what is symmetric? What is a skew-symmetric? So symmetric means that the transpose of the matrix is the same as the matrix itself. So swapping rows and columns is not going to affect anything, okay? So this is when we call the matrix symmetric. Well, clearly, if we want matrix to be symmetric, so since this is m by n, this is n by m, two matrices are equal if and only if all the entries are equal. And for that, the only way for this to happen, it has to be a square matrix. Because an m by n and n by m, when m and n are different numbers, are not equal, okay? So first of all, it is only defined for square matrices. And now, what condition do you need? As I said, swapping the rows and columns does not change anything. So what does it mean? It means, let's say this is a 3 by 3, 1, 6, 4. The elements that are mirror image of each other with respect to this diagonal, they should be the same number. So here, let's say if you have a 4 in row 1, column 2, you have to have the same number 2 in row 2 and column 1, 4, right? Or if you have, let's say, a 5 here in 1 and 3, in 3 and 1, you have to have 5. If you have a 3 here in 2 and 3, you have to have a 3 here in 3 and 2, okay? So these are that are mirror image of each other with respect to the main diagonal should be the same number. So if we want to write it, we say Aij is the same as Aj when I is not equal to j, okay? That's the definition of a symmetric matrix, and it has some important properties that later we'll see. Then skew-symmetric is what? Skew-symmetric is when you transpose the matrix, the result is going to be negative of the original one, or -1 times the original one. Okay, so this is called skew or anti-symmetric, sometimes called. Okay, so if you hear the word anti-symmetric, also it means the skew-symmetric. And for this to happen, again, the matrix has to be square, definitely. And since all of the entries in A are negated, and they are the same as the transpose, it indicates that the elements on the diagonal should be all 0. That's the only way that when you make them negative, they are the same as the original numbers, because the elements on the diagonal, they are not swapped, right? Only the elements off diagonal are swapped. The diagonals are going to stay. They are not changing their position because of transpose operation. And so if they want to be the same as their negatives of themselves, then the only solution is these numbers are all what? 0. So then any number off this main diagonal, which is all 0, has to be negative of its mirror image. So here, if you have a 1, here you have to have a -1. Here, if you have a 3, here you have to have a -3. Here, if you have a -2, here you have to have a +2, okay? So for a skew-symmetric matrix, first of all, Aii equals 0, and then Aij is equal to -Aj when j is different than I. Okay, that's called a skew-symmetric matrix. Again, they have some important properties, and we use them a lot. One of the places that we use them, and we'll get to this later again, but we can define for a vector, if we have a vector like, for example, omega, which has 3 components, omega x and omega y and omega z. If we have a column vector like this, we can define for it a skew-symmetric matrix, S of omega. Okay, this is a skew-symmetric operator, really, that acts on this vector, and it gives me a 3 by 3 matrix. So first of all, it should only act on 3 by 1 vectors, no other dimension. The input that you pass to it is always a 3 by 1. Again, we call this the skew-symmetric operator. And when you define it for a vector omega, the result is going to be a skew-symmetric matrix 3 by 3, where of course all diagonals are 0. And then the off diagonals are negative omega z, omega y, negative omega x. And then here you have omega x, negative omega y, and omega z. Okay, so this is the matrix that you define, a skew-symmetric matrix that you define for a vector. Okay, now so what? What's the use of this? Well, I'll show you later that, for example, if you want to carry out a cross product between two vectors, right? So let's say you also have a vector r, which has 3 components, rx, ry, and rz. If you carry out a cross product like omega cross r that you use a lot in dynamics, right, to get the velocity term due to rotation, and this, instead of doing the cross product, you can multiply the skew-symmetric matrix of omega by vector r. So you convert a cross product into a matrix product. And this makes life a lot easier when we are doing these calculations and we try to do everything using matrices. Okay, so this is one of the properties. It has a lot more properties, this is skew-symmetric matrix, but here is one of the applications, and let me briefly and fastly show you in MATLAB. So let's say here omega, I show it with w, is equal to 1, 2, and 3. And r is equal to, let's say, 0, 5, and 7. And now the skew-symmetric matrix of omega is equal to, as we said, it is 0, negative omega z, then omega y. Then we have positive omega z, correct? You can easily follow this format. So it's positive omega z, which is 3. Then we have a 0, and then we have negative omega x. Then we have negative omega y, positive omega x, and 0. So it looks like that. Okay, now if I say what is this cross of omega and r, that's the result. If I say what is SW times R, that's the same result. You see, so instead of me doing the cross product between omega and R, I multiply the skew-symmetric version of omega by R. So it's a simple matrix product versus the cross product. They are the same thing, okay? But we'll see more and more application of that as we go forward. So I have covered this. Finally, time derivatives. So if your matrix has elements that are not constant numbers, or some of them might be, but some of them are, let's say, functions of some variables that themselves are functions of time. Let's say, for example, you have x as a function of time and you have y as a function of time. Then if I say your matrix A is something like this, x squared, and then xy, and then 3, and then let's say negative y. Okay, if I say what is time derivative of A, it means apply the time derivative to each and every one of the entries. So what is the time derivative of x squared? Well, clearly you have to use the chain rule, so it is going to be 2x times x dot, or dx over dt. What is here? Here you have a product, so it's going to be dx over dt times y plus x times dy over dt, correct? 3 is just a constant number, it doesn't have derivative, so it's 0, and that one is going to be negative dy over dt. Okay, so that's the meaning of taking a time derivative from matrix A. Good. So hopefully this was useful to you, and let me tell you one other thing, a function of a matrix. That might also be useful to you because I know you might see something like that. So if I give you a function of a matrix, like for example, exponential of a matrix, okay, or let's say functions of matrices. So let me show you a couple of those as well because they might be useful to you. So when I say, for example, I have A, and A is like 2, 3, 4, 3, 4, 2, and 1. And then say, what is e to the A? Okay, what is exponential of this matrix? Well, it does not really mean that I raise e to the power of each one of these entries. This is not the same as this. Okay, so if you have such a thing, what you need to do is to use the Taylor or Maclaurin series. So if you remember, e to the x was what based on Maclaurin series? It was 1 plus x squared over 2 factorial plus x3 over 3 factorial plus all the way, correct? So in that case, e to the a is, instead of 1, you have to use I of the same dimension as a. So if a is, for example, n by n, this is going to be I n by n, then plus a, then plus 1/2 of a squared, which is actually a times a, and then 1 over 3 factorial, which is 6, correct? If you want, I can write it this way for you. And a to the power 3, which is like a times a, and so on and so forth, right? So calculating exponential for a matrix, you have to use the Maclaurin series, right? So keep that in mind. Or if I say, what is, for example, sine of a, you're not gonna get sine of each and every one of the entries. You say, well, sine of a, since I know sine of x is what? It's, if you remember, correct, sine of x was what based on the Maclaurin series? Sine of x was x minus x cubed over 3 factorial plus x to the 5 over 5 factorial and minus x to the 7 over 7 factorial and all the way. Sine of a is going to be a minus 1 over 3 factorial a to the power 3 plus 1 over 5 factorial a to the 5, and so on and so forth. Okay, so keep in mind that when I define functions of a matrix, I'm not going to simply apply that function to each and every one of the entries, okay? That's completely wrong. I have to use the definitions of Taylor or Maclaurin series, especially Maclaurin, and basically write that function, whatever it is, in terms of polynomials of a. Because that's the only thing I can do on a, is to raise a to some power and multiply it by a scalar and then add the results together. Okay? And clearly when I want to do that, my A matrix has to be what? A square matrix, because otherwise I cannot raise a to any power, right? Remember when we defined power 2, 3, we said matrix has to be square. So when you define these functions on matrices, first of all, they are square. Second of all, you write your function in terms of polynomials, and then you try to calculate it, okay? So let me show you an example of that as well for you. So if I have, like, for example, matrix A is equal to 1, 2, 0, and 5. And I say, what is exponential of A, right? Now, if you look at MATLAB, Does MATLAB give me the thing that I mentioned? No, because if you know, this number is e. That's the Euler number. So it raised really e to the power 1. So what it did is exponential 1, exponential 2, right? You see this number here? That's this guy. Exponential 0 and exponential 5. So what MATLAB did is the one that I really do not want you to do. Just raise what? Each and every one of the entries, e to the each and every one of entries. Or what if I say what is sine of a? Again, if you look, this is like sine of 0, this is sine of 1, and 1 means 1 radians, right? So when you say sine of 1 means 1 radians, you see that's this number. So MATLAB is trying to calculate it that way, but the matter of fact is it's not really that, right? So if I want to calculate it, let's say a was what? A was 1205. And here I need to calculate exponential of a. Let me just call it f. So this f is equal to I 2 by 2. By the way, I in MATLAB creates an identity matrix. And then add to it what? All of those other terms, right? So first I set it equal to this, and then I say for I equal to, let's for now just add 10 terms, see what happens. F is equal to whatever it was plus what? Plus a to the power I, correct? And actually it goes from 1 to 10 because we need power 10. And then this whole thing divided by factorial of I. Right? And I can keep showing it on the monitor, right? So we see the result as I changes from 1 to 10. So first it's just 1001, and then let's see what happens. So here we go, CLC clear, and we run this guy. So take a look here. When we first start with I number 1, you get this one. You go I number 2, you get this one. I number 3, I number 4, 5, 6, 7. And after some power, if you take a look, you see that the numbers are barely changing. Look at this. This number is the same as this one. This number is changing some decimals. Now when I go forward, you see this number is still changing. That number is not changing anymore, right? This number is increasing, but the increase is reducing. This number is still increasing, but it is reducing in the amount. So still they are increasing. So maybe I need to go from 1 to 20 and see what happens now. So now if we go and if you look at the last set of numbers, look. If you look at here and here, here, you see that this number is changing now only in the third decimal. This number is changing in the third decimal between these two. When I go here, now it's the fourth decimal, third decimal. Now I go, it's the fourth decimal. Now I go, it's even below fourth decimal. So it seems like it is converging really, right? After 20 terms, it's not changing anymore. So it doesn't really mean that I should really keep going forever. After so much, these extra terms, these higher powers are literally like zero contributions. Okay, so it will converge. You do not need to keep calculating forever. After so many terms, the difference between each matrix and the previous one is only going to be very marginal, and you can stop. Okay, so now you can say, for example, up to 4 decimals, this is the result, right? Correct? And now the question is that going to be exponential of 1 in the first element? Yes. Is that going to be exponential of 5 in the last element? Yes. right? If you look, and this guy was what? If you look at A, that is, so it goes 1, 2, 0, 5. This is 1, that's right. This guy is not 2. Look at this. This guy here is not 2. So exponential of 2 is what? 738, but this number is 72. This 148 looks like exponential of 5, but not this number. So you see, although some numbers might look like they are really exponential raised to the entry only, so this is exponential 1, this is exponential 5, this is exponential, that's not exponential of 0, right? Because exponential of 0 is what? 1. So if I really want to do it, I had to say what? Something like this: exponential 1, exponential 2, exponential 0, and exponential 5, correct? If I wanted to just raise each exponential to each element. This is going to be the final result, not this one. You see, 2 entries look like, but not all of them. And the reason that those 2 are like that is because here I have this special 0 number. If I change that to 3, now you're not going to get anything similar. So let me take a look at this one. So here I'm going to change that number to 3. Now let's do it again. And when I do F, I also want to show you the exponential of those numbers, okay? So we can have them side by side and compare them. Right, so we're going to look at the last F. Hopefully it converges after 30 terms, and this one, right? So let's do it. Okay, so let's see first whether F is converging. If you look at the decimals, you see 4 decimals, they are the same number. So it definitely converges. And now if you compare, look at this one and this one, there is not even a single number in them that are equal. So although clearly F converged after probably, if you look at the numbers, you'll see that, let's say here, yes. After here is the time that it's not changing anymore. Before that, you still have a little bit of change. And at least until 4 decimals, right? So it takes probably 20 something, right, for it to converge. But for 4 decimals, but this one is definitely different. Okay, so hopefully I could make my case clear that when it's a function of a matrix, you're not going to apply the function to each and every one of the entries. Use the Maclaurin series or Taylor series, and you use the polynomials of A. Okay, hopefully this video was useful to you. I will see you in my next lecture. Thank you.